Good morning, welcome back. We were looking at the incremental circuit of the common gate amplifier, and we took the circuit in all of its with all of the non-idealities, including the channel length modulation R0 resistance and source resistance for the current source, which is Rs, right? And we calculated what I out by I in is, and then you decided that in order to make this equal to 1, you can impose a condition on GM, R0, Rs and all of that, right? So, you can think about it, and we can also assume that, for example, R0 is infinity, and then play with this and see what happens. Okay. But one thing that you could do, for example, is to take the limit of R0 being infinity and Rs equal to infinity, and then this expression becomes fairly straightforward to write out. Okay. Now, what we can do is to look at the input and output resistance of this circuit. So, I am just going to copy this circuit. Any guess as to what the input resistance will be? Will it be high or low? And similarly, output resistance, any guess as to what it should be based on what we are trying to design? Input resistance should be low, and then output resistance should be why? Because it's a current controlled current source. Okay. So, that is what we should get. Let us see if we get that. I am not going to calculate it, I will leave it for you people to calculate. I will just point out how it should be done, I will give you the answers, okay, because we should move ahead a little bit. Actually, we have done the calculation for this. Once I draw it, it will look very, very familiar for you. Okay. So, I am going to do R in and R out. So, now where should I look at R in and where should I look at R out? Right. R in is, so if I take a line there and a line here, then your R in is basically looking in from, that is your R in, and that is your R out. Right? Any difficulty? Did I goof up? RS should be? RS is what? RS is part of the source, no? So, this Rs and Is, right, they are it's a non-ideal current source. It's just a mathematical representation of the current source. So, the Rs is sitting inside your current source. So, you can't separate that out. So, the R in is what the combination of the current source and that source resistance sees, correct? And then R out is what the load sees. Okay. Now, quickly to calculate R in, what will you do? Okay, let us, how do you calculate R in? Come. So, when you are looking at R in, what do you do to RL? Okay, in principle you have to account for RL also, but let us not worry too much. Okay, you calculate it with RL. I will give you the answer without RL. Okay, because I have not done the calculation without RL, with RL. Okay. So, what do you do? So, actually without, okay, so you calculate it at home. Okay, I will give you the answer without RL. Okay, if RL is 0, right, in that case it is actually very straightforward. You can find out R in to be equal to 1 by GM parallel R0. Okay. So, now somehow that RL will come, okay, that you calculate. Okay. Now, if RL is 0, the reason it becomes simple is that what will happen if RL is 0, you will have this kind of circuit, right, and then this is grounded, and then I have this R0 here, which is going from this to ground, right, and you can replace and you want to find out things looking in from here basically, right? And this is identical to R0 and GM, correct? And what is this? GM times Vs, and Vs is this well, right? So what is this going to be? GM Vs. We have done this many times. What does this current source now look like? It looks like a resistance of value 1 by GM. Okay, at least from the answer you should be able to tell me that, right? So in the case when RL is 0, it is very straightforward. When RL is non-zero, you calculate it. Okay, all right. That is your input resistance. Let us do the output resistance. Okay. Did everyone get that? What do you think R out will be? High, low? Okay, meanwhile, you guys start calculating R out. Yeah, all of you have already done it. In fact, when we did the common drain amplifier, the input resistance of the common drain amplifier is very similar to the output resistance of the common gate amplifier. Go and look back in your circuit, you will see how that happens, right? Because in the common drain amplifier, where were you giving the input? What did I say? I said if you go back, right, and look at the common drain amplifier, right, where was the input? Okay, not the common drain, sorry, the other one, this voltage controlled current source, voltage controlled voltage source, or what, sorry, should not, oh yeah. So we had this voltage controlled current source, right? And where did we calculate the input resistance and all of that? Where did we calculate resistance? So this was R out, and then you look at R in calculation. Where is R in calculation? We didn't calculate R in? I gave that as a, sorry, yeah, this R out calculation, right? You are looking at it from the drain. Is it similar to what we are doing now? Right? That's essentially what we are doing, right? Is it or not? No. So it's sorry, it's not this one then. It's the other one. Okay. So it's one of these which we have done. Now I have also got a little confused. Let me just see. Okay, forget about that. We just calculate it again, right? It's very straightforward. You can go and figure out which of these it was earlier. R out, how do you calculate R out? Kill I in, but you retain RS. Okay. That's what I thought, but it's okay, let's not go back and confuse everybody. Okay, so if I kill this, what will happen? I have that here, then I have that this way, R0, and you excite it with a test source and you look for the current that is flowing here. Correct? This is the source, this is the drain, and this is your R0, this guy is your RS. Correct? This we have done earlier actually, and you can very easily do it, right? And this one will work out to what? So your R out, please do this and see that this is what you get. You will get R out, R0 plus RS plus GM RS R0, which essentially is RS into 1 plus GM R0 plus R0, right? Show that this is the case. I am not doing that, but it's very straightforward. Okay. Basically, what do you have to do? This current is here. You have it. This guy is what? GM times Vs. Correct. So there's a current which is flowing like this. You have I test. So what is the current in this loop here? It will be I test plus this, right? I test plus GMVS. And what's the current flowing here? It should be again I test, right? Then what do you do? Then you just go through this loop. You start from 0, go up to V test, go through this R0, come here, come down here, and you will know what Vs is in terms of this. You put all of that, you will get this. Okay, very straightforward. We have done this many times. Okay, so the interesting thing is that this GM-R0, right, you can assume is much greater than RS, right? So this is approximately equal to GM-R0 RS. Yeah, again now R0 is going to be much smaller than GM-R0 RS. So what is happening is that you now have a current buffer whose output impedance, right, is much higher than your RS. Your RS was the impedance that your source itself provides. That impedance has now got multiplied by a factor of GM-R0. Okay, so this guy is high. Okay, so basically this last bit we went through a little quickly. Just go over it peacefully. It's very straightforward. For any circuit, you should be able to find out what is its input impedance, what is its output impedance, what is its gain, and also what is the frequency characteristic. Yes. Because everything was done with GM being infinity, no? So GM is large. So this GM R0 and R0 also is going to be large. So obviously GM times R0 will be large, right? So you can neglect 1 with respect to that. Okay. All right. Now let's go to the frequency response. The frequency response of this amplifier is very interesting, and it's actually something that all of you will be happy with. I'll tell you why. Yeah, we discussed it yesterday. So, all right. So the next thing we should do is the frequency response, right? All right. Now for the frequency response, let's take the incremental circuit that we have first without any capacitors. So I have the device, I have this connected, and now I have eaten up the load. So just be careful. Sometimes I am putting an RL, sometimes I am eating up the RL. Okay. In any case, you can work out the details. The general details don't change. It's only the specifics which will change. Okay. Because sometimes including all of that makes your calculation very complicated. And as in frequency response calculations, we typically don't assume any R0, right? Because that will trouble us. So we have this. Okay. So in this thing, what are the terminals? That's your gate, drain, and source. Okay. Now go back to your Mosfet, which is actually a 4-terminal device, right? We have done this many times. I have my gate, I have the drain, I have the source. Tell me the capacitances again, Prakhar. What is this capacitance? CGD. This capacitance? CGS. Then anything else? I have my bulk terminal, and I have, this is CDB, and this is CSB. Okay. Now in this particular circuit, where will bulk be connected? In this circuit, bulk we are going to connect to gate. Yeah, because bulk is connected to ground, right? It so happens that gate also is connected to ground. So correct, what she is saying is right. Okay. Bulk is connected to the most negative point of the circuit, right? And in the incremental circuit, what is the most negative value? 0. So it's connected to 0. For our course, that's what it is. For us, for this course, bulk is always connected to 0. Okay. In more advanced courses, people do interesting things. Let's not go there. Okay. That is correct. The difference, for example, in the common source amplifier, source also was connected to ground, bulk also was connected to ground, so CSB got shorted out. In the common gate amplifier, you will see that some other capacitance gets shorted out because, for example, gate is connected to ground, bulk is connected to ground. So something will get shorted out. We'll see which one that is. We'll put it in here and it will become clear. Okay. So now that we have this particular incremental circuit, let's draw it in terms of the the dependent source, and let's not worry about putting it in that horizontal picture. We'll have it in the vertical kind of orientation itself. Okay. Gm times 0 minus Vx. This guy is your Vx, correct? And I have a source, and I have this. That is your Rs. In. Have I missed something? Vs is 0. Yeah, so let us leave it like that. Sorry. Yeah. Correct. Right? That is 0 minus Vs. And then what else do you have? That is connected to ground. Okay, now populate these capacitors here. This is not Vx, sorry. This is 0. Okay. Now, this was actually Vg, right? And that became 0. Okay, populate the capacitors. Where do the capacitors go? So I have so just name the terminal so that everything is all right. So I have this to be my drain, right? That is source and that is gate. So first one is CGD. Okay, what happens to CGD? Does it survive? No. Why? Because both sides are ground, right? Gate is ground, drain is ground, so CGD disappears. Okay. Next capacitance. CGS. Right? CGS. So CGS will survive. Okay. What about, so we have finished CGD, we finished CGS. Let's go to CDB. Where does CDB appear? CDB will appear between drain and ground. So it's going to appear between this terminal, and we'll put it and then remove it so that everyone's happy. So that is CDB. And what happens to that guy? That fellow also is not there. Okay. Then, so we have finished CDB. CSB. Where does CSB come? Ground and source. So it's going to come here, right? CSB. Okay. Can you look at this and simplify this circuit? Careful. Look at the various nodes and tell me. Don't just guess. Look at all the capacitors connected to the various nodes and tell me what happens. Right? So both are in parallel, right? Does everyone see that? Anurag, do you see it? Yes? Okay, what are the two capacitors in parallel? CGS and CSB. Why is that? You have this S terminal here, right? And you have, this is ground and this is also ground, right? So CGS and CSB both appear here. So I couple that and I write this as CGS plus CSB. Okay, and this guy is nothing but, this is 0, right? GM minus Vs. So again I can just flip this guy and put this way, and this will become GM times Vs, and Vs is this value. Correct? And where is your I out? I out is flowing in here. Okay. Now can you analyze this circuit? Does this look particularly simpler than the other things that we have done? No. What do you mean? Who said no? Okay, how many nodes are there in this circuit? 2. One node is ground, right? Only one effective node is there. So at that node you just write KCL. So what is the current entering? In is the current entering that node. What are the currents leaving? GMVS plus, this is what, RS, plus Vs by RS plus what? So let's write it in terms of Yeah, let's not write it in terms of R, right? Let's write it in terms of G. So Vs Gs and then S times Vs times Cgs plus CSB. Correct? So, and then what is your I out? What is I out? GMVS. So now can you simplify this? So Vs is nothing but In divided by Gm plus Gs plus Cgs plus CSB. Which one? Okay. Other way around, no? Why did GMVS? Because In is entering here, right? Look at this current. This current is entering, that is your In. And what are the currents leaving? GMVS, Vs by Gs and SVS into CGS plus CSB, right? And then you have I out is nothing but Gm times Vs. So from this equation you work out what is Vs in terms of In, right? So I was writing it correctly only. Vs in terms of In is this, and your I out is S. Good. You will get an S grade for that. So your I out is nothing but Gm times In divided by Gm plus Gs plus S times Cgs plus CSB. Okay. So what are the characteristic features of this? What's the order of this transfer function? 1. All your previous transfer functions, what was the order? 2. So this is definitely easier, right? Okay. Now what is the approximation you can make to get some feel for this?
Send Gm to infinity.
No, don't send Gm to infinity straight away. Okay. What is CGS? CGH is much greater than CSB. So you can drop CSB with respect to CGS. Okay. Then what about GS and GM?
GS is very less than GS.
Huh?
GM is very greater than GS.
You can make that approximation, right? Because if you did not have all these capacitors, then this expression is is going to be Gm by Gm plus Gs into In, and you want this to be equal to 1, which means you are working in the approximation that Gm is greater than Gs. So with these two approximations, what happens to I out? Becomes essentially becomes I out by In becomes Gm by Gm plus SCGS. So which is nothing but 1 divided by 1 plus S CGS by G. So the bandwidth of this amplifier, of the common gate amplifier, is Gm by CGS. Okay. Now can you tell me something about this bandwidth? Do you think this is more or less than the previous ones? Go back and see. What did we have? Somewhere we did it, right? Where did we do it? Here. So let's just put everything on one page. So the bandwidth of the common drain, common source we had. Now we choose another color. Some people don't like the fact that I am making my notes like a kindergarten student's notebook, but anyway. Common gate bandwidth is what? Gm by CGS. Okay. Out of all these, what did we say about these two? The bandwidth of the So we already had said that bandwidth of common drain is much greater than bandwidth of common source. And what do you think about this one? What do you think about GM by CGS with respect to this one? Right? So clearly CGS is more than CGD, right? So that way, that means there's a tendency for this common gate bandwidth to be what? Less or more? More or less? So typically this will be more, okay? Common bandwidth of the common gate is usually more than this, because you have to, it's actually not a fair comparison. You have GM here and you have 1 by RS and all of that, right? So if you put in the numbers, basically GM can be much greater than GS, correct? So that can compensate the fact that CGS is more than CGD, correct? So it turns out that this is the way it works out. Also, it's very interesting. Let's just take this GM by CGS and work out something about that GM by CGS. This is a very important characteristic of any device. So when people talk about, I'm making a, companies which make transistors, Intel, TSMC, various companies. So every kind of transistor they design, they give a figure of merit. And that figure of merit is called the transition frequency. They call it as FT. Okay. And FT is so you want to compare two things, right? Something that works say at 3 gigahertz, something that works at 6 gigahertz, something that works at say 20 gigahertz, or like what Swaroop, his work is all in the range of 30-40 gigahertz. Okay. Today transistors are available which have an FT of close to 1 terahertz. They're trying to push it to close to a terahertz. Terahertz means 1000 gigahertz. Okay. So from this bandwidth of the common drain of the common gate amplifier, you can actually get some very interesting inputs. So let's just see that. Okay. So we worked out that the bandwidth of the common gate amplifier was GM by CGS. Okay. Can someone tell me what is the expression for GM? Okay, so what was your ID? ID was mu n Cox W by L into VGS minus VT whole squared divided by 2. Okay, what was the GM? Dou ID by dou VGS. And what is this? Mu n Cox W by L into VGS minus VT. Okay. What is your CGS? In saturation, what was CGS? Long ago we worked it out. Remember. Okay. Did we say this? We said it was 2/3 WL into Cox. Correct? I gave you this expression long ago. Don't look like this is somewhere from Mars. We did this. Okay. When we first did the common source amplifier frequency response, we did this. Okay. Alright. Now put these two in and work out this GM by CGS. What would GM by CGS be now? Be mu n Cox W by L into VGS minus VT divided by 2/3 WL into Cox. So what will happen? Cox goes, W goes. Okay, this will become 3/2 into mu n VGS minus VT divided by L, okay, into 1 by L. There is a WL because Cox is this Cox has units of what? This is per area. So you are multiplying it into the gate area. This is the area. Right? This has units of per 1 by area. Okay. So now if you look at this, okay, can someone, so you have your Mosfet, right? What does the Mosfet look like? You have something like that. This is your source, this is the drain. Correct? And you are applying a voltage VDS. Correct? Now it so happens that this quantity, this VGS minus VT by L, right, this is essentially some kind of field, right? This is a voltage divided by length, right? So this is like a field, electric field, right? And mu n is nothing but mobility. So this is like an electric field. This is your mobility, and you will learn later that mobility into electric field actually has dimensions of velocity. Why is that? You can check. Mobility has dimensions. What are the dimensions of mobility? Okay, you won't know this. It is centimeter squared by volt second. Okay, and the dimensions of electric field would be volt per centimeter. If you put this in here, you will see that mobility into electric field will have a dimension of centimeter per second, which is nothing but velocity. So what you are saying is that this Gm by Cgs, which is called the omega t or the transition frequency, right, is nothing but some velocity divided by length. So in a sense what it's saying is that it refers to the time that this particular electron takes to go from source to drain. So in very crude terms it tells you how fast your transistor is. Okay, so this omega t is a very important metric for transistors. You have another metric which is called Ft, and Ft is nothing but 1 by 2 pi omega t, and Ft is in hertz, right? Omega t is in radians per second. So Ft is usually the parameter that people say for various transistors. So you guys are buying transistors, right, for your experiments for the CAD lab. So go and look at the data sheet for that transistor and find out what the Ft is. It will be interesting. Okay, you guys are buying cheap transistors for doing small work. Ft of that possibly would be in the 10 kilohertz, 100 kilohertz range. Okay, maybe 1 megahertz maximum. Okay, all right. So that covers the frequency response of the common drain amplifier. Sorry, common gate amplifier. So to summarize, what does the common gate amplifier have? Gain 1. Input impedance low. Output impedance high. Frequency response excellent. So it's a very good current buffer. Okay, so what have we done? We have done the common gate amplifier, which is a very good voltage buffer. The common gate amplifier, which is a very good current buffer. The common drain amplifier, which is a very good voltage buffer. Then we did the voltage controlled voltage source, and what are we left with? Current controlled voltage source. So that's what we'll start now. Alright, so we now go to the last kind of control source that we want to make with our MOSFET, and that is the current controlled voltage source. Okay, for the current controlled voltage source, what do you expect your Rin to be? 0. Very good. What do you expect your Rout to be? 0. Very good. Okay, so we want to make something whose Rin is 0 and Rout is 0. Okay, so it's a current controlled voltage source. Remember, this is a controlled source only for incremental quantities, which means that if you have an incremental input, which is the current, right? So you have an I in and you need a V out. So what should be the multiplying factor? it effectively will have dimensions of resistance, right, or impedance. So it will have there will be an R here. So let's call that as Rx. Okay, and what kind of function does this actually represent? It will be a trans what amplifier? Trans impedance. Actually, when we did the voltage controlled current source, we didn't mention this. What amplifier should it be? Yes, so that is a trans conductance amplifier, because over there we had I out as V in into Gx, and so that was a trans conductance amplifier. This is a trans impedance amplifier. It converts an input current into an output voltage. So typically these kind of things are used, again, that day we took the example of a photodiode. So that gives you a current. You want to convert that current into a voltage. Many of you may actually do some experiments with photodiodes now, right, for the CAD lab. Some people who have interest in that, okay, who might have found a circuit for that. Okay, so you have this. Can someone figure out what kind of comparison we need to do? Again, this is a feedback amplifier, right? So what do you have? What do you have, and what do you want to get? Right. So what is you have a current, correct? And what do you want to do with the current? Exactly, right? You want to, from the current you should make it into a voltage. So once you take the current and make it into a voltage, you will get a current controlled voltage source. Okay. Okay, so I have an I in, right? I pass it through a resistance. What will happen then? I will get a voltage, and I compare that voltage with V out. So how can you, so basically you want, when the feedback is operational, you want V out minus I in times Rx to be 0. Okay, that's what you want to ensure. So how do you do that? Exactly, right? So you take let me take some resistance, okay, and I'm just going to put the I in down here. So I'll pull current like that. You could have done it the way you were saying also. That's the many ways of doing this, right? You have I in and you have Rx. So what is this voltage going to be? What is the value of this? No. If this is I in and Rx, what is the value of this guy? Nominally, this will become I in times Rx. Correct? And what do you do? What do you want to do with this? You want to compare it with what? V out. Okay. So essentially you want to do V out minus I in Rx. So how can you do that? This thing? Oh, this is wrong. This is wrong. Wrong. Wait. Sorry. Okay. This is I in Rx. Okay. So I have I in, pass it through a resistor, I will get I in Rx. Now I want to implement this function V out minus I in Rx. So what can I do? So I can make this guy V out, I in Rx, and then I can look at this quantity Vx. So this Vx would be V out minus I in Rx. And what should you do with this Vx? You have to compare it with 0. That's essentially what you want to do. Okay. So what can you do? So you want to use this Vx, right, to do something. What should it do? Okay. Okay, remember what you have. What do you have with you? Okay, let's write down what we want to do. Okay, what do we want to do? If if V out is greater than I in Rx, what do you want to do? You want to decrease V out. You can't decrease I in. I in is given by God, right? V out is what you're trying to generate. So if V out is greater than I in Rx, you have to decrease V out. And if V out is less than I in Rx, you have to increase V out. Correct? So now you want to increase or decrease V out. But your Mosfet, what is the Mosfet? The Mosfet itself is only a voltage controlled current source. That is, it can measure two voltages and it can change the current. This is your Mosfet. So how do you change a voltage when you have only a current? You can put a resistor, that is one thing, but there's actually a simpler idea. If you take any node and you pump in current into that node, what will happen to the voltage? It will increase. You remember all these parasitics are sitting there, right? So if you take a node and pump in current into that node, the voltage will go up. And if you extract current out of a node, the voltage will go down. Okay, so you can use that idea. You have the Vx. Vx is now your controlling quantity, and basically what do you do with the Vx? Let me say that I connect another current source over here, okay, which is a controllable current source, and let me call this I, right? Let me say this is I1, and let me say that this I1 is proportional to Vx. What will happen now? See if this feedback works. If V out is greater than I in Rx, what will happen to V out? What do you want to do? You want to decrease V out. Now because I1 is proportional to Vx, right? This is your Vx, right? Vx is V out minus I in Rx. So if V out is greater than I in Rx, Vx is greater than 0. So basically you will pull current out of the node V out. So you will decrease V out. Okay. So this essentially becomes your current controlled voltage source. Okay. This is what we will now convert into a transistor. We will do that tomorrow. Okay. So this gives you your current controlled voltage source. Think about how this thing operates. What I would suggest you do is that go back and look at the 4 sources that we have done. Voltage controlled current source, voltage controlled voltage source, current controlled current source, and current controlled voltage source. And just explain to yourselves how that feedback loop works. Okay, do that and come. It will just take you 10 minutes and it will clarify a lot of thoughts. Okay, so these various circuits that people use are in a sense just an implementation of some feedback idea. Okay, that is the thread that connects all of these things together. Okay, so let's meet tomorrow. We'll finish off this current control voltage source, and we'll be done for the quiz. And